Recent advancements in emulating atom cavity systems has allowed us to study non-equilibrium dynamics of cavity spin systems, specifically the Dicke model. In particular, we have used the atom cavity system to realize the discrete time crystals in the Dicke model, which is a dynamical phase associated with the discrete time translation symmetry breaking of the system. We have also used the system to observe the Cosme mechanism in open Dicke model. This mechanism relates the formation of topological defects on the speed of the finite quench across a second-order phase transition. Despite the ever-increasing literature in DTCs and Cosme mechanism, a lot of gaps are still needed to be addressed. For instance, the parametric resonance picture of the DTC in the Dicke model, which explains the period doubling instability of the system at resonance, remains incomplete. This is because the effective parametric oscillator picture of the Dicke model predicts unphysical, exponentially growing solutions at resonant driving. Furthermore, it is yet unclear how nonlinearity and dissipation stabilizes DTCs. As for the Cosme mechanism, observing it in the open Dicke model is interesting since there is no defined notion of topological defects on it due to it being an effective zero-dimensional model. Furthermore, the Cosme mechanism has yet to be generalized in the dissipative systems. In order to resolve all of this, we will need to consider a system that A can be reduced to a single driven Dicke model, and B is a minimal system that can host topological defects. For this, we consider the one-dimensional Dicke lattice model, which is an array of Dicke models coupled by photon-mediated nearest neighbor interaction. In my thesis, we resolved the problem of the parametric resonance picture of the Dicke model by considering the role of nonlinearity in stabilizing DTCs. We also explicitly show that the open Dicke lattice model follows the Cosme mechanism, showing that indeed we can generalize the mechanism to dissipative cavity spin systems.